Okay, class, as promised, here is your Chapter 10 lecture, which covers joins and overlays. I apologize that I had to cancel class last night, but I had a family situation come up. I had to drive about a 5.5 hour round trip from one of the hospitals here in West Virginia, and there just wasn't any other way to do it. I rattled my brain and tried to come up with alternatives, and there just was none. And so that was the only option we had. But I will do the lecture just like we would have done in class. And I will try to make myself more available in the next few days to next week. If you need any assistance, you have trouble, you can't schedule an appointment because it's too far. It's not far enough out that you can get one in or something like that. You want to talk, discuss about something, send me an email and I'll try to work in some time where I can help you. Now, here's the thing. If you're going to do that, don't just say, I'd like to talk to you next week one day. Give me some times and days. My general times and days are Tuesdays, Wednesdays, and Thursdays from 3 o'clock to about 6:30. If I don't have anything scheduled, I can work you in. And if you need to talk outside of that time frame, for example, over the weekend, Saturday or Sunday, or even Monday, put those times that you're available to speak if you want. And then I'll try to find whatever works for you that works best for me, and then we'll move on from there. But don't give me just one option because that may not work. So give me a couple. All right, I'm going to talk about joins and overlays. Joins and overlays are pretty quintessential to basic GIS. It's how we bring together different sets of data to solve problems. So what are joins and overlays? One primary use is to combine layers of information. Example here we have slope, and we have rock confidence maps, and we're trying to figure out where landslides could happen. And we know based on certain types of rocks and certain types of slopes lends itself towards landslides, but we don't have a map of where landslides could occur. So what we can do is, by using joins and overlays, we can combine these two sets of information and basically create new knowledge. And that new knowledge being, in this example, that overlay layer that has both bits of information. So this is kind of review back when we did other joins stuff with tables. It's pretty straightforward. Find a field that was common to both data sets. Didn't have to have the same name, but has to have the same information. It wouldn't have to say state FIPS, but it had to have the state FIPS numbers, and then it would join that stuff together and create all that data together. Spatial joins are a little different. Spatial join, the records are matched using a spatial relationship instead of a certain key like a FIPS number. Relationships are the same spatial operators that you've used for spatial queries. Intersection, proximity, and containment. You're trying to remember what that is. Intersection, something crosses something or touches something. Proximity, it's the closest thing to it. And containment, something is inside of something else. Spatial join using intersect. Parcels is a target table. So a new parcels feature class is created. The zoning records that intersect each parcel is attached to the parcel in the output table. So essentially what you would be doing in a situation like this, you've got parcels and you've got zoning. So parcels, it says, is your target. Parcels is where you kind of start. So what you really want is to have the zoning data for the parcels. So by using the intersect, whatever zone goes over the parcels, that data is then joined to the parcels. You could also do proximity. The classic example is cities and airports, where you could join the airport data to the cities that are closest to it, or you could summarize and join the city's data for each airport. Depending on how you do this, you get two very, very different outputs. One is a simple join, one is a summarized join. You can also use containment. Here we have septic systems and geology. Septic is the target, so the new septic feature class is created. Each output septic system is then assigned the geology that it falls into. So it takes your existing data set for septics, makes a new septics data set that has the geology with it. Comparing operators, in this example, the intersect and within operators give nearly the same result. Intersects are what's within. They would only differ if a septic landed on a boundary. The within operator would give you a null value, meaning it couldn't tell you what to do because it was on the boundary. The intersect would have two matches, so that would potentially create a problem too. But that is the general gist of it. All right, so I'll try to do this again 3 different times now. I've started on this slide and the phones rang and I had to stop. When we talk about cardinality, it can get confusing. Mainly because the idea of a target and a join and which is what and how or where things are going. But this illustration kind of helps with that. The target is the data set that you want to add information to. So in our example, we have this other data over here, and we want to join it to this data. So the stuff that we want to join, we're calling the join table, and the thing that we want to add it to becomes the target. So think of your data here being aimed at the data over there, so that's the target. This works out really great if you've only got one thing here to join to one thing there. Less so when that's not the case. And as it says here, as for table joins, one-to-many cardinality must be dealt with because the tables cannot be joined directly. So when you have many things here that you're trying to join to one, and they call that one to many, which to me it should be many to one, but that's another story. The issue is you can't do that. You can only take one thing here to one thing here. So when you have a situation like this, where you're trying to join information from all the cities in Washington to a polygon of Washington, you have to do something called a summarized join. So let's look at kind of the way this works. Spatial joins come in 2 types to offer options for handling one-to-many cardinality. You can create multiple copies of the target feature until there are enough for each matching record in the table, or you can summarize the multiple matching records in the join table using a merge rule, creating a single summarized record that can be joined to the feature target. The second one's what you're going to do for most of the time. The multiple copies option is called a one-to-many join type because of the target features may have many output copies. The merge rule is the one-to-one join type because each target only has one output. Don't confuse the join type with the cardinality between the tables. It is common to do a one-to-one join on a table with a one-to-many cardinality. Yeah, you have a one-to-many cardinality, you summarize the data and complete the join. And you don't have to do the summarization, the software does. So let's look at cardinality of parcels and zones in an example. Parcels usually lie within a single zone, so it's expected cardinality is many to one. A parcel in 2 zones would be an exception or a logical consistency error. And a one-to-one join works well, and no merge rules are needed because only one zone record should exist. It is expected to match each parcel. And if that's not the case, you get a null value, which is then something you can go look up and try to fix. Cities and airports is a great example. If the cities and airports, okay, let me try to say this again. In the cities and airport example, only one airport can be closest to a city. So that's one-to-one cardinality. Is expected. Identical distances would be a really rare exception. A one-to-one join works well, and no merge rules are needed or anything because it's just, that's all there is. If distance exceptions yields 2 matches, you get a null value, meaning that something's not quite right. Cardinality of septic tanks in geology. Again, one-to-one is what you're expecting. Lies on a boundary, that would be a rare exception. Again, it'll tell you something's wrong and it'll give you a null value. Highways and soils, if you wanted to determine the soil characteristics for each highway and help plan maintenance schedules. Each highway is expected to cross multiple soil units, so it's a one-to-many exception. A one-to-many join would create multiple copies of each highway to match every soil unit it crosses, which really is not very helpful. A one-to-one join type with merge rules works for this problem. Each field from the soil table can be assigned a merge rule to summarize the information from the records to match each highway. In other words, if a highway crosses 3 soil types, you could take the attributes of those soils, and if they're numeric, you could summarize them or something like that. So let's look at these merge rules a little bit for one-to-one. The join count indicates how many soil units matched each highway. So just like we're talking about there, it would give us this count. So there was 3 soil types for this piece of highway. This is the target FID, the highway, and all the stuff. Now, if we had clay and slope and all these things, it would average this out across all the soil types. If it was in a hydrographic group, I'm not sure exactly how it came up with this, but it would look at this join and see if it tells you that there's 3, it would tell you what those 3 are. So that could be useful. The other option is a classic overlay. So here we're looking at 1 of 2 options. Overlay of slope and rock competency yields a feature class with fields from both. It's useful for assessing landslides. The original slope and competence polygons are split and combined to create new ones. Each new polygon receives a unique combination of the data from both data sets. And you get that pink one down there at the bottom, that polygon. It's a combination of the 2 polygons above and has all the information from both of them because it splits features and it basically avoids one-to-manys and makes everything become a one-to-one. As far as the different types of overlays, intersect and union. Intersect only keeps areas that overlap. Only the polygon regions within the circle remain as the output. So data set 1, data set 2, data set 3 is everything that was in this one, that everything from this one that is within this space once you overlay, or this. That's basically how it is. Union keeps everything from both inputs, whether they overlap or not. Not all areas and both inputs are retained in the output. All areas are retained. So you get everything. So in union, the usual goal is to combine all the data and the extent of the data sets is typically the same. The combined table can be queried. You can look for combinations of values and things like that. Sink hazards where you have limestone and low slope. Rockfall where you have high slope and high competence. Landslides where you have low competence and high slope. Whatever the case may be, these combinations of events, you can identify them. In intersect, the usual goal is to find overlapping areas where certain conditions hold, things like suitability analysis. Queries are performed first to find suitable conditions, and then you select features or then intersect to define areas of this example snail habitat. Elevation, limestone, conifer. Only thing that you're looking for is stuff that's in the range you want here, in the limestone here, and the forest type here, and that ultimately gives you your snail habitat. Intersection and geometry union can be performed with 2 polygon inputs. Intersection can be applied to all geometry types. A line in polygon intersection can assign geologic unit information to streams. A point in polygon intersection can assign school district information to houses. So in these examples here, you have a stream. It basically cuts the stream everywhere it goes across and changes from your other data set. Each part of the stream is then assigned the information from that part. Similarly here, points and polygons, if a point falls in this polygon, it gets the data from that polygon. What do the outputs look like? Well, it can be a little bit different. Different output geometries may be chosen depending on the input. You join polygons, you can get polygons, lines, or points. You join lines, you can get lines or points. You join points, or you join polygons and lines, you can only get lines and points. The bottom line is when you put 2 things together, you can get the same thing or less detailed physical structures. So a polygon's more complex than a line, a line's more complex than a point. Think about it like that. So if you join two lines, you can get lines. You can get two polygons. If you join two polygons, you can get a polygon, a line, or points. Lines are less complex, and so you can only get lines or points. That's sort of the way. Whatever your least complicated thing is, in this example here in C, you have lines and polygons. You cannot get polygons from this, but you can get lines and you can get points, because these are both less complex than that and the same or less than the lines. But you can't get anything more complicated than the lines because that's one of your inputs. Alright, so let's look at extraction versus overlay and see the difference. Clip and erase are essentially the same thing as intersect and union almost. Very similar, I should say, not the same. But the big difference is intersect and union keeps your attributes. So when you do an intersect and you get an output, it has all the attributes of both data sets. When you do a union, it keeps everything and all the attributes of everything. When you do a clip, you simply use this as a means of cutting this. It extracts part of the data from the original data set, but does not include anything from what you used to clip with. Erase is sort of the inverse of clip. Instead of giving you the area that matches your clip, it gives you the leftovers, if you will. Cookie dough. That's how I kind of think about it. Data quality and spatial analysis. Data quality can significantly impact the results of a spatial analysis. Truer words have never been spoken, I think. Tract boundaries should coincide with county boundaries. These two data sets are not logically consistent and they do not match. This creates something we call slivers. These are things that should line up that don't. They increase the workload as far as the processing. They're also problematic in that some analysis will have difficulty with that. They'll screw up intersections and containments and stuff all the time because you'll be looking for something that intersects something over here, but you got a little sliver, and all of a sudden, guess what? Now it doesn't. So having data that is spatially all on the same scale, that coincides as it's supposed to, is important. You can control a lot of this with XY tolerances. They can be used when you're developing things to reduce slivers when you do your overlays. So if something should line up but it's not, you can kind of make it shimmy around there a little bit to help. So the XY tolerances that we're talking about in this example, as you see here, they'll kind of fix everything except for that really large pink one because it's just too big. The downside is all close vertices get collapsed. Using a tolerance will degrade the accuracy and precision of the data set overall. So it is a little bit of a conundrum. You have to decide whether degrading the entire data set is more important than preventing the generation of slivers. And so essentially it depends on what you're trying to do with your data set. And if what you're trying to do will be significantly complicated or impaired because of the slivers, then degrading the overall data set might be a reasonable answer. If the slivers aren't really going to cause you any problems, then that's really probably not the best way to go. Areas and lengths. You've heard me say this before many, many times in 200 and probably before in this class. Areas and lengths are not updated automatically. Only in certain circumstances are they. So we'll kind of go over this. When you do an overlay, it often changes the shape, the area, the perimeter, and the length of features. So when you do an overlay and it clips and cuts and modifies things, stuff changes. When you project things, stuff changes. When you change projections, stuff changes. Okay? When you basically do any geospatial function on a data set, something changes. Almost everything doesn't get updated. There are a few exceptions. In a geodatabase field, shape underscore length and shape underscore area are automatically updated. So what does that mean? I've got a feature class in a geodatabase. If I have a length field that's called shape underscore length, or an area field that's called shape underscore area, those get updated automatically. If I have a length field that's just called length, or a shape field, or an area field that's just called area, they do not. If I have anything other than a feature class in the geodatabase, it's not going to get updated automatically. Other than these two file or field names that you see right here where my mouse is dancing around, other than those, you can assume if anything has ever been done to that data set that those measurements of area, length, perimeter distance, whatever it is, are incorrect. And so you need to use the calculate geometry tool on the attribute table to update those values and to make sure that they are correct. I just assume everything's wrong and fix it. So how do you set up a spatial join? Stepping through the series of questions can help you determine what it should look like. And so this is kind of the way that Price walks you through it. You think about your final output layer or table, what is it supposed to look like? Okay? Whatever it's supposed to look like, what I mean there is you're taking some other information and adding it on to something else. So it's going to look more like the something else. That something else that you're adding the data to, that's going to be your target. Then think about your spatial operators. What's appropriate? Is it intersect? Is it a union? Is it a proximity? Is it containment? You have to think about that kind of stuff so that you choose the right options. What fields do you actually need or want? If you can get rid of stuff that's not going to help, go ahead and do it. Could a target feature have multiple matches? If it does, how are you going to address it? Is that going to be a summarized join, or maybe you need to rethink what you're trying to do and come at it from another approach? Maybe you're setting your join up wrong. Instead of having maybe you've got your target and your join flipped, and so you got to turn them around. Or maybe not. Maybe you do need them summarized. You need to really be cautious of that because you get some dramatically different outputs, and understanding what those are can be very important. So here we have an example. A congressional staffer must provide a list of representatives from districts with at least 10 deaths from earthquakes. Seems kind of obtuse, but imagine you're serving on some congressional committee that is trying to properly allocate earthquake preparedness funds, and you're trying to come up with a metric for where that money should be, or if there should be additional funding in certain areas, and so you come up with this. If at least 10 people have died from an earthquake in that area, it needs more funding than other locations with fewer deaths. That's kind of a threshold they set. And so he has a feature class here of districts, these are congressional districts, and a feature class of earthquakes with deaths and damage information. So in doing this, ultimately you want to be able to take the earthquake damage and the district information and combine it to identify what you need. That means you have to join the earthquake information to the district information. So districts would be your target, your earthquake data would be your joins. So in this example here, districts is the target, earthquakes is the join, records should match. If the quake touches the district, so intersect with work, and you can read through here talking about the different fields that matters, what they're really looking for, and add those over here, and just like that, you get your outputs. You get your results. The output table shows that the district ID, the state, and the representative name, the party, the sum, and all that. Districts with no earthquakes have a null value for deaths and damages, because if you didn't have an earthquake, you can't have earthquake damage or earthquake deaths. So you get some nulls over here. But you could then, for example, look at some of this stuff and see here, Don Young, representative Republican from, I think that's actually Alaska. They have 125 people have died from earthquakes there. So that's kind of it. I mean, um, I wish there was some magic bit of information that I can tell you that'll make this all make sense and you won't have any trouble. I just tried doing some joins the other night in class and literally got myself confused about it because it can be so confusing. More so in Pro than what it was um, in desktop. But work through the exercises from Price, work through all the tutorials, and then do all the exercises. And in the quiz format there for the lab, the exercises portion there, um, I give you specific methodology on how to do the ones that you need to answer for points. And the other ones you can answer for practice. But this is one of those things that's kind of like riding a bicycle. I can tell you how to ride a bicycle, and I can show you how to ride a bicycle, and I can hold the bicycle and let you get on it, and you can start pedaling. And that's kind of where you're at when you go through the tutorials. And by the end of the tutorials, you can ride the bicycle. Okay. That does not mean you're ready to go riding cross country. It doesn't mean you're ready to enter in a bicycle race or something like that. It doesn't mean that you're not going to crash your bicycle really quickly. It just means that you understand the concept of cranking the pedals, steering the handlebar, and trying to balance it so you stay on two wheels and your head above your feet. But at the end of the day, doesn't make you Lance Armstrong or a rider on the Tour de France just because you know how to ride a bicycle. It's the same way with joins and overlays and queries and a lot of the stuff we do in GIS. You learn how, but you only really get good at it through doing it a lot of times. And so hopefully by the time you work through the tutorials and the exercises, we're not going to make you the Lance Armstrong bicycle riding champion of GIS, but we're not going to make you a 7-year-old that just learned how to ride for a $5 bet and goes about 30 feet and then runs into a bunch of azaleas. Um, we're going to try to get you somewhere in between. We're hopeful that by the time you've done this in the prior classes and then you've done this using this software in this class, that what you end up doing is being able to navigate around. You're not going to be perfect at it. You're not going to get it right every time, but you should be able to tell when you got it wrong and then go fix it. It'll be awkward. It'll be challenging. Think of it like first dates. It's not always going to be smooth, and sometimes it's not going to work out like you thought. But ultimately, you will get better at it, and ultimately with this, you will too, unless you just decide to give it up and stop doing GIS. But hopefully this will help. As always, watch the tutorials from Price if you get stuck. And if you have questions, email me. Make sure you give me specifics about what you're asking, because it can be a little bit challenging sometimes when you say things like, I'm having problems with question number 2. Okay, well, which chapter? Is it a tutorial question 2? Is it the exercise 2? What part of question 2? Yeah. What is question 2? They're the kind of things that sort of help. All right, well, hopefully that'll get you through. And like I said, if you need help, things that you want to talk about this week class, because we weren't actually able to meet up because of my situation, um, feel free to email me, contact me, set up an appointment, or ask for an outside of my regular office hours appointment. Try to be as accommodating as I can since it was my fault that we didn't have class. So this should help. Work through your tutorials, do your other things, and we'll see you next week.